Sagar, good evening. I am very fine. Vivek, how are you all? Good evening, Ashish. Jai Hind, Rudraksh. Good evening, Anjali. Good evening, Namaste, Robert. Good evening, Akshat, Bharati, Matthews. Good evening. So let's start the session. Yesterday homework first. Okay, homework question. Firstly, uh, tomorrow anyway it's a doubt session. So what I do is that because it takes minimum half an hour of time for better explanation. So what I will do is that adder question, 15 nanoseconds question I have given now. I don't know how many of you have done that. We discuss tomorrow in the doubt session. Yeah, no problem, no problem. Very good, very good. Those who got 50, it is very good. So those who don't get, don't worry. So next homework question. I have given another homework question which is based on carry located. Okay, good evening, Rahul. Yes, if you try, that is sufficient. Whether you get the answer or not, it doesn't matter. If you try, that is sufficient. Now, see here. The carry located at a circuit. Yeah, no problem, Ashish. All your doubts we discuss tomorrow. That is homework part I gave. You just leave it night. Tomorrow we discuss that. Okay, Ashish? Yeah, I will implement and show. Don't worry. Again, this marker. 1 minute. Why this pen tab is not writing? Yeah, fine. So yesterday I have given this homework. Edi Namaskaram. This is a carry generator circuit. Here we have used one XOR gate and AND gate. I hope you remember yesterday class. It requires 2 nanoseconds. This AND OR operation, not 2 nanoseconds, so 2 time units. 2 gate delays, and this part requires 2 gate delays, and this carry is given to T. And both are XOR operated, you get the sum. Okay, so this requires another 2 gate delays. Total how much? 6 gate delays. Anybody has done this with less than 6? Yeah. How many of you have done with 5TC? If you are having that answer with you, just attach that image. I will check whether you are right or not. With 2 inputs only. With 2 inputs only. For multiple may be possible. Let me check with 2 inputs whether it is possible or not. First slide, Aditya. Abhijit, first slide only. Okay, let me show you. I told you you can do propagate carry by 2 methods. Go by A XOR B, one method. Otherwise A plus B. Is it clear? This point you remember or not? Yesterday class I told propagate carry can be implemented by XOR gate or by using OR gate also. Do you remember or not? Please tell me. So using that logic, you can take here for propagate carry this one, and for This one you can use AND gate. In that case, your delay will be reduced to 1 TC. For AND OR, it is how much? 3 TC. Now, what about this part? What about this part? For here. Okay. Can I take like this? Those who have already done, can I take one XOR gate and say 2 TC? Yes or no? I hope some people have done this. Those who got the answer 5, this is your sum, this is your carry. Yes or no? No, it is not correct. If you take like that, your exclusive OR gate, okay, that is wrong answer. Please understand. Okay, your when what is your sum is? Please listen. What is your sum is? A XOR B XOR C. You can apply this only when this part is equal to P. When this part is equal to P, then only you can take directly P XOR with C will give you S. This is valid only when P is a XOR gate. But here P is OR gate. Na? Okay, you cannot use this. Logic is clear or not? Sum is A XOR B XOR C. Okay. When your P is A XOR B, then you can say P XOR C is your sum. But here it is not correct. Everybody accepted or not? So because of this reason, how you implement here is like this. Ruchita, please understand your sum is yesterday class. You should remember sum is A XOR B XOR C. Okay. If your P is A XOR B, then you can say sum equal to P XOR C. Provided P should be equal to how much? A XOR B. Similarly, here if you have C and here you have P, then in that case you can say it is XOR operation of these two, like here. But in our problem, in the second method, I am not doing like that. I have taken OR gate. OR gate is A plus B. You take here A and B, you get A plus B here. You should not have sum as A plus B XOR C. What is your sum is always equal to A XOR B XOR C. Okay, so you cannot implement like this. This is not valid now. Okay, fine. Now, what to do? You directly implement it. What is there? What to do is take A XOR B with one XOR gate here, and for this you connect your C and calculate will give you sum. Okay, now you understand. Every time in the according to that question, XOR gate requires yesterday class discussion. This is not new, this is continuation to the yesterday class. Okay, this is 2 TC. Now you already calculated now 1 plus 3. At what time you get this one? This is TG, 2 TG. Total how much? TG and 2 G. At what time you get this one? This will come at 3 TTG and this will come at 2 TG. And this requires another 2 TG. So what is the total answer? Out of the two, whichever comes late, that you consider 3 plus 2 total 5 TG. This is the implementation. Okay, your sum is always equal to, I am repeating this part, sum is A XOR B XOR C. For that, what I am doing is I am not taking propagate carry. Propagate carry can be A plus B also. So propagate carry I implemented by A plus B, which reduce my delay here. Then I got the carry with 3 delays. By that time, I calculate A XOR B and make it ready. Out of 2 and 3, whichever comes late, we will should wait up to that. 3 plus another 2. Total 5 delays are required to generate the sum. Earlier, how many delays are required to generate the sum? 6 delays. You observe the difference between the first figure and second figure. Here each XOR gate is 2 T delays, 2 gate delays. If it is okay, I will move to the new question. What is your problem, Rishi? Please ask me. Okay, this is your carry. You should remember yesterday class compulsory. Carry can be generated by propagate and generate carry. Using these two functions, you can generate the carry. Then what is your sum? A XOR B XOR C. Okay. What is INCN? Please type properly, Rishi. Whatever gate increment doesn't matter. It may increase or not. That is not my question. Gate may increase. That is, there is no limit in the question. Yeah, I am saying for least propagation delay. Gate increase does not increase your propagation delay. So you have 100 gates like this. All are parallel, only one delay. In the series, if you connect only 3 gates, it requires more delay compared to this case. XOR gate is made using the available gates. Ganesh, I don't know whether you were there in the yesterday last part of the class or not. That's why we took 2 delays for XOR gate. Why you take XOR gate 2 delays? Because you are making this XOR gate using the available gates that we discussed yesterday already. Okay. Rishi, please see. Up to this time, 3 delays. Never see number of gates more delay. That is not the required condition. Here, how much you should just calculate the time. It depends on the connection. You assume A and B are applied at time t equal to 0. It requires 2 delays to get this. It requires 3 delays to get this. Out of 2 and 3, whichever takes more, 3 plus another 2, total 5. Okay. Out of the 2, you should wait for which one will take more time. For that one, you should wait. Then plus another delay. It doesn't matter number of gates. If you like, if you say number of gates in this inside, n number of gates are there. I don't know, Aman. I already told you yesterday. What is that? Propagative. Please listen. Please revise your class before coming. Every point we discussed in the class. I told XOR propagate carry can be replaced by XOR gate or OR gate. No, Sushil. I don't know why you people are asking this. You remember yesterday class question or not? All gates are one delay only, but you have only AND gate, OR gate, NOT gate, NOR gate, NAND gate. Okay, XOR is not directly available, so we made XOR with the available gates. If you remember, something like that. Okay, so then we decided that for XOR it requires 2 delays. Okay, XOR is made using this. That is your job, Samira. Please listen. It is impossible to write all the 30 slides in one slide. So always after 2 hours of the class, it is available. Okay. After 2 hours of the class, your PDF is available. Just quickly review the PDF fastly. Right. So if it is a topic, I generally give some conclusions if there is something to remember. Okay. So let's move to the next part. Multiply. We have done adder, subtractor. The next one is multiply. 2-bit okay, 2-bit binary multiplier. First, you should remember how to make multiplication. You know, A is a 2-bit number, A1, A0. B is another 2-bit number, B1, B0. I want to multiply A into B. Okay, I want to multiply A into B. Acha, I will see. Okay, we'll do questions today, but last what PDF is there now. For that key I will provide. Please remind me once. 30 questions I have given, but key is not provided by me. Please remind me. I will give you. So please see here. At the end of the class, please remind. I hope you remember the basic multiplication. What is A1 A0 into B1 B0? Tell me. Multiply this B0 into A0 and B0 into A1, B1 into A0 and B1 into A1. For a single bit, multiplication is nothing but what is 0 into 0, man? This is nothing but 1 bit multiplication is equal to AND operation only. Will you accept it or not? Is it same as AND operation? Very good. Now, remember carefully, listen here. In this process, add this. How to add this? This will come as it is. I hope you remember the basic additions. This is B0, A0. What about the addition of these two? When you do addition of two bits, okay, B0 A1 and B1 A0, addition will give you two results. What are they? Addition will give you two results. What are they? Very good. Sum and carry. And again, you do the addition of these two, you get the sum and carry. Addition will give always two results, sum and carry. Sum is always equal to XOR operation, carry is always equal to AND operation. So shall I make this figure like this? A0 and B0, you give it to AND gate. Then B0 into A1 and B1 into A0. 1 minute. B0 into A1, B1 into A0. These two will give to one AND gate. These two you will give it to one AND gate. Now for getting sum, what to do? XOR operation. Okay. Now for getting carry, what to do? AND operation. That we take it back. Okay. And now again this is C2 and B1 A1. You give it to another XOR and another AND gate. This is your final answer. Sum S0, S1, S2 and C3. Okay. So this is the simple implementation of binary multiplier circuit. You can also draw this figure like this. Please see B0 and A0. You give it to an AND gate. Then B0 A1, B1 A0. Now these two you give it to one half adder. It will give you sum and carry. So sum and carry. Again B1 A1. This is another half adder. Sum and carry. So this is your S0, S1, S2, S3. I have not done anything new. Just I implemented this. For addition, sum is always equal to XOR operation. Carry is always equal to AND operation. Why half adder comes here? Because you are adding two bits, two digits, B0 into A1 and B1 into A0. You are adding this and this. When you add two, the addition is always done with the help of half adder. Arithmetic operation, please remember that. So just to see the figure, if you have any doubt, please ask. What happened? No comments are coming. Yeah. Just I kept that XOR gate and AND gate in a box, then it will become half adder. That's all. Okay. So this expression only. If you do these two XOR operation, what is that? C2 and what is that? C2 and B1, A1, you do XOR operation sum. If you do AND operation, carry. If in place of S3, you can say carry, right? Yeah, right. You are adding here only two bits now. Okay, Rahul. Next. Now, one minute. Yeah, if it is 3-bit, we definitely pull it. So I will give you another method. Please see. You have A1. You take this as B1, B0, A1, A0. Okay. Now, please listen here. It is, I want to multiply A into B, okay, which will give you Y3, Y2, Y1, Y0. 4-bit is because you are multiplying two bits number, the result will be how many bits? 4 bits. Y3, Y2, Y1, Y0. Can you tell me what is the multiplication of 0 into 0? It is all zeros. Can you tell me what is the multiplication of don't fill totally 2 into or 2 into 3? Don't say 1011 multiplication. Please read A1, A0 as one number. 10. How much it is? 2. 11. How much it is? 3. What is multiplication of 2 threes? Yeah. Please listen. Okay. Don't read like this. Sir, 1011. So one bit is 0. Na, sir. All answer is 0. No. 10 means 2. 11 means 3. 2 threes how much? 6. 6 means what is the answer? 0, 1, 1, 0. Lastly, 1, 1 is 3, 1, 1 is 3, 3, 3 is how much? 9. So like that, fill the table, find Y3, Y2, Y1, Y0 by K map. This is also another way to implement the multiplier. What is y3, y1, y2, y0 is nothing but ab. Y3, this will give you multiplication result of a into b. Okay, this is one way or this is one way. So try this method also if you want. What is the reply? What is your doubt, Silvam? See here, I'm repeating here. Please see, this is your B. This is your A. It is a 2-bit number. It is a 2-bit number. Multiply AB. You get a result of 4 bits. Is it okay? So, for example, you read these two. It is 0, 0, one number. This is another 0, 0, one number. Multiply, result will come. Similarly, you take these two, 1, 0. These two, 1, 1. 1, 0 is 2. 1, 1 is 3. 2, 3 is 6. 6 means 0, double 1, 0. Similarly, 1, 1 is 3. 1, 1 is 3. 3, 3 is how much? 9 is the answer. Like that, you fill this whole table at home. Then find y3, y2, y1, y0. 4 K-maps will come. Simplify it to get the answer. Right? So the next part we are discussing is we did arithmetic part. Now we did do a simple logical part, that is comparator circuit. So the next part is comparator circuit. Okay, in that first one bit comparator. What is comparator? It will just compare whether the two bits are equal, greater, or less. Three things you can compare. What are they? You have, let's make one table. Yes, yes, yes. A and B, we have X, Y, Z. AB can be 0, 0, 0, 1, 1, 0, 1, 1. Okay. So let us assume X will say A greater than B. Y will say A less than B. Z is called A equal to B condition. Let me fill this table. Let me fill this table. Okay, your comparator, magnitude comparator is op amp. That is also true. Now see here. 0 and 0, both are same or different? What happened here? Same or different? Same. So I should say it is not greater than, it is not less than, it is equal. Okay. Next. Next. Tell me. 0 and 1, greater than or less than? So it is not greater than, it is less than, it is not equal also. Next. 1 is 1 and 0. 1 is greater than 0, but less than, not less than 0, not equal to 0. Lastly, 1 and 1 again they are equal. Done. So what is x here? It is 1 only here. What does it mean? It is a b bar. Very good, very good, very good. What is y? What is y? It is 0, 1. That is a bar b. What is z? It is here and here. That is both the cases. A bar, b bar plus ab. You can say a, x nor b. So now let me implement this circuit. Now listen here. A B bar. What is this? A B bar, which will tell you X. Next, similarly, what is A bar B? What is A bar B? You take inverter here, that will give you A bar. Now, if you take OR operation of these two, what is that? If you take OR operation of these two, what will you get? A bar B plus A B bar. But I need a inverse, that is X NOR. So instead of OR, I will take, don't worry, I will modify it. Okay, now see, is it okay? If you take OR operation, it is XOR. So let me take, what is that? NOR operation. You can directly take X NOR also. Now it is okay. It is a NOR gate. A bar B plus A B bar whole bar. That is nothing but A XOR B whole. So this is what we call one bit magnitude comparator. In one of the gate exams, same question is given, but instead of NOR gate, they gave bubbled AND gate. You can say same or not, bubbled AND gate or NOR gate. Any case it is same. So that is one bit comparator. Now listen. 2-bit comparator circuit. Okay, so you have a 2-bit number A, which is A1 and A0, and another 2-bit number B, which is B1 and B0. Okay, so please listen here. If a particular bit AI greater than BI, single bit, we represent that with X. What is X? It is given by the equation AI into BI bar. That part is already done. Yes or no? Similarly, if AI is less than BI, I represent that with YI, which is AI bar BI. If AI equal to BI, then it is represented by ZI, which is AI X NOR BI. I hope this is what we discussed earlier. Now, what we are going to discuss is it is extend these relations for 2-bit. So when will you get A greater than B? A greater than B can be done by two cases. First case, please listen carefully. Out of the two bits A1, A0, B1, B0, two 2-bit numbers, when can I say directly A greater than B? If A1 is greater than B1. Direct MSB, if A1 greater than B1, you need not worry about A0 and B0. Happily, you can say A greater than B. This is one possibility. Or another case. What is the another case? Is both may be same. Okay, both may be same and A0 greater than B0. Very good, Rohit. Right. So is this line clear to everybody? How to say A greater than B? First bit should be more. Otherwise, first bit may be same, but second bit is more. Two cases. So you can say X1 or Z1 into X0. Similarly, can you tell me what is A less than B condition? Reverse. In place of greater, you keep less. Some simple. A1 should be less than B1 or A1 equal to B1 and A0 less than B0. That is Y1 or Z1 into Y0. Lastly, A equal to B. When it will be true, A equal to B, both bits are same. That is A1 equal to B1 and also A0 equal to B. What does it mean? Z1 must be true and also Z0 must be true. Then only you can say A equal to B. So these are the conditions you can say for A less than B, greater than B, or equal to B conditions. So substitute those equations, solve it, you will get the answer. One method. Otherwise, firstly clear this part, then I can go further. Krishna, A greater than B, you have two 2-bit numbers like this. When will you say A greater than B? Tell me. This is your A, this is your B. Just mathematically, forget about everything. Tell me, when will you say A greater than B? Krishna, please tell. First, you should check these two bits. If it is 1 0 and 0 1, blindly 1 is greater than 0, sir, A greater than B. Here 1 0 like this. In second case is what? They are same, but this is more. Then only I can say A greater than B. Okay, two possibilities are there. It can be 1 or 0, don't worry. First case is check whether A1 greater than B1 or not. MSB is more or not. No. Then check if they are equal. Check the next bit. Then only I can say A greater than B. Krishna, please see. Tell me if it is clear or not. Krishna. Now, let me explain the same with another method. Method 2. Listen. This is A1, A0, B1, B0. Just fill X, Y, Z. You should only tell me first. X, Y, Z. Can you tell me the first case X, Y, Z? Tell me A greater than B or equal to B or less than B. Very good, very good. It is A equal to B. Second case, A less than B. Third case also A less than B. Fourth case A less than B. Now fifth case. Fifth case A greater than B. I mean next case. The next case is again equal to B. Can you fill this table? Please don't see bit by bit. See two bits together. Two bits together. Okay. So it will give you okay. Lastly, A equal to B. Okay. So I only fill this. What is X? Sum of the min terms. Which min terms it is 1? 4, 8, 9, 12, 13, 14. What is Y? Sum of the min terms 1, 2, 3, 6, 7, 11. And what is Z? Sum of the minterms 0, 5, 10, 15. In one of the gate paper, the question is how many times X occurs, how many times A greater than B occurs, how many times A less than B occurs, and how many times A equal to B occurs. This will occur for 4 times. This will occur for 6 times. In all possibilities, I am saying this will happen for 6 times. Okay, your homework is very simple. Minimize, okay, X, Y, Z using K-maps. Can you do this? Someone asked me some doubt. What is that? Alicha, what is that? Sir, 1-1 kaisa liya? Kaha 1-1? So many 1-1s are there, yeah? Alicha, which 1-1? 11. It is a min term. Please see here. For Y, what is that Y? 1011. 1011. What is the min term corresponding 1011? Two Adityas are there, yeah? 1011. That's why always Adityas are asking because two Adityas are. 8421 code. You can remember this. What is the trick here? Nothing trick. Okay, just mind may remember 8421. Automatically you remember it. Very simple. 10. Okay, 8 plus 2 plus 1 is 11. Your doubt is cleared. Can I give you names as first Aditya and second Aditya? Okay. Now B greater than A how? You tell me only. I don't say. First, always please ask your doubt properly. Otherwise, if I explain something else, it will waste my time, your time, and all the people who are watching also. Completely ask it in the first time itself. You ask me why it is 11 first, then why it is greater than. You ask it in the first time itself. It will save our time. Okay, now you tell me, Aditya, B greater than A or B less than A. You tell me. This is your B. Don't say. Don't see one bit. Read two bits together. What is this number? What is this number? 3. What is this number? 2. 3 is more or 2 is more? 1 means 3. 10 means 2. Tell me 3 is more or 2 is more? That's all. Very good. These two are A and these two are B. Very good. Let's move further. Now, very important topic we are discussing now, that is switching circuits. Definitely one question compulsory every year, examiner's favorite. Compulsory one question comes from this part, what we call multiplex. Okay. Its pet name MUX. We call it as a MUX, multiplexer. Every year you see one question. Without this, examiner don't sleep. Okay, any year one question compulsory comes from this. So I have divided this into different cases. We discuss all the possible cases from this. You will be definitely able to that question 100%. Okay, I never say that from every topic one question comes. Okay, from marks I said earlier I said. Okay, so because I know things won't happen. So now listen here. What is marks? Okay, before going to marks, just understand why you are going for this multiplexer in practical orientation, not only for your exam. So let's have some practical understanding of what is mux, why mux, etc. So earlier, yesterday class you made one circuit like this AND gates, so many inputs, connections, big complex circuits you are made. Assume you take some discrete gates and connect with some wires. You have wound with wires and made these gates like this. Connections are made with the hand. With the hand, you made these connections. What is the disadvantage? Different wires will have different lengths. They may give you different propagation delays. One simple answer. Second case, there may be some loose connection in any one of the wire which will damage your whole operation. So it may be difficult to troubleshoot that. It may be complex. Okay, different issues are there here, different lengths, everything. It may be complex, difficult to troubleshoot from where it is going to where, all those things. So instead of that, if you are able to have one box, you have some kind of magic box. Okay, you have a magic box. In this box, you give just ones and zeros, nothing else. It will do whatever job you want, it will do. Say for this magic box, you say, I want full ladder. Okay, it will say, give these ones and zeros here, I will do this. I want full subtractor. Same magic box. You just change these ones and zeros, it will work as a full subtractor. Okay, you give its ABC inputs. Okay. So like that, if you are able to have some circuit, definitely it will be advantage for you. Yes or no? There is one box. Externally, you are only making ones and zeros. Internal is fixed. Internal to fix out. It is able to implement any given logic function. What is the advantage? Your circuit connections are robust. Okay. You need not every time check for the connections and all those things. That part is already done in that magic box. That box can be named as integrated circuit, which contains a medium scale integration circuit called as MUX. So mux can be used to implement any given logic function easily. I will prove it. Don't worry right now. Just I want to give you the reason why we are studying mux. So mux can be used to implement any given logic function. That mux circuit will come in the form of integrated circuit. Externally, you do some modifications. You are able to implement any function like a universal gate. You can say, right? So if it is okay, then we can move further. Okay, so let's see the basic definition of the mux. Right. So just see here. Thank you, Arun. So mux is a combinational circuit which contains many inputs and single output. You have so many inputs, but only one output. Based on the selection input, it will select any one of the many inputs and transfer to the output. Let me draw its figure technically how it looks. Definitely, I am not, Arja. You can say maybe Boolean. Because of Boolean algebra only you are able to do anything. De Morgan didn't made much things. Yeah, he just made that De Morgan's law. Instead of that, you can use Shannon law or this one also. Duality principle also will give you that. Now, so you so this is how your mux looks like. You have a 2 power n inputs, y minus 2 power n input lines, n selection lines. These selection lines will help to select any one of these 2 power n and give it to the output. So your input is waiting with 2 power n number of lines. Out of them, your selection lines will select any one of them and give it to the output. This is what we call mux. You can also show with a normal rectangle or converging symbol because it is many to single. That's why it is converging. So like this also you can see. You have 2 power n here and you have n selection lines and one output. Mux is many to single, many to one circuit. Based on the selection input, it can select any one of the many. Okay, and another point I want to specify is it can be used to implement logic functions also. Yeah, I will show you what is that, Sushil, what is inside the mux. Okay, just you understand this box will do this job. Then I will prove and I will explain how this box, what is inside this box. If I say magic, you don't believe, I will give you logic for that magic. Okay, don't worry about it. I will prove the logic behind this magic. Okay, selection line is the name who will select your input. Selection line is the name who will select your input line to give it to the output. Because here you have, say for example, 16 lines. Out of these 16, who should be selected and given connected to the output? Out of the 16, whom you want to pick and connect to the output, that is given done by this selection. Okay, so let's take one small practical or day-to-day life examples where you can use this mux. So fundamental job of mux, you understand, it has many inputs, one output. See this simple example. What happened? Now listen, very simple, good example you can visualize. You have some kind of system, your iPod, laptops, different sound systems are connected. I will be using one multiplexer which will select any one of these by based on the selection lines B and A. It will select the source and it will connect that line to this system. Who is giving input to this system is maybe your this system, this one mp3 or laptop or your satellite or your cable tv. Who is giving that is decided by this multiplexer. You got the picture? Who is doing that? This fellow is doing. Okay, so I read your mind. So multiplexer, your theaters are also called multiplexers. Earlier days many movies are used to play. Yes or no? I am saying earlier days. See, because of this corona, your multiplex movies, everything became ancient days. This is in digital. Now, if you see in analog also see here, this is one example. So you cut any, you close any switch, your op amp will transfer that particular signal, that particular amplification. R4 by R by this, R this by this. If you are CSC, just close your eyes for some time. I mean for this. This by this gain of the op amp is selective here. It's not summing amplifier. Here it is a selective gain. You can select the gain of RF1 by Rin, RF2 by Rin, RF3 by Rin, or RF4 by Rin. Accordingly, your magnitude will change. Okay, here physical switches are there, mechanical switches are there. This is also one kind of multiplexer only. Then let me show your communication. Okay, time division multiplexing you call. You have four sources. One source at a time we use. First you send A, then you send B, then you send C, then you send D. Then computer science people can also understand in your computer networks. You might be studying this also, and EC people in communication, electrical people in this class. Okay, you have the four inputs. So first I will make some rotating switch here. One in first I will connect to A, then B, then C, then D, then again B, C, D. At the receiving end, I will use one circuit called demultiplexer, which will do exactly reverse. I will explain that. Now, why that likes are increasing to 600? What's happening? Okay, so please listen. At the receiving end, you use one demultiplexer, which will just to do reverse job. You have many to single, here single to many. This data is to be given to which receiver? Target 1000 or what? Okay, this is the best example of earlier days. Please listen. Happening here in our class also it came or what? Oh, remember the class first. Listen here, concentrate. You can make it later. Earlier days and ancient dates, if you remember, you have telephones like this. Now also you might be using. So these telephone channels are connected to one multiplexer. You see, for example, you have 100 users in here and another 100 users here. What here? I think I need to refresh. Okay, just 1 minute. Pen is not working. Hmm. Okay, leave it. Don't worry. You can do it in the free time. Even I will also enjoy because when I'm explaining, if you do that job, what is the problem? Other people will lose its concentration. Okay. So listen here. Don't worry. Whoever does it doesn't matter. Okay. So listen, please. First, earlier days you have telephone lines. Say in a city you have 100 or 1000 users. In the other city you have another 1000 users. It is not feasible to make from every 1000 another 1000 direct connections. Is it possible? Tell me, here, is it possible? 1000 into another 1000 connections or 1 lakh into another 1 lakh connections? Impossible. So what we do is we just calculate the peak bandwidth, how much it is required. Not all the 1000 users may not be talking. Some maximum, maybe some 100 people may be talking at a time. We calculate the maximum peak traffic. Accordingly, we make the channel available bandwidth. So here we use multiplexer. When a person wants to make a call, we will select that person and connect to the line in the available. Then this line will come here. At the receiving end, you have n number of receivers whom you want to call. That will be connected. Okay, like that. You can say in your communication TDM, etc. also. Okay, so like that you will be making your connections. Okay, so this is what we call some basic examples of mux. Earlier days, if you remember, during New Year, every single person in the city wants to call, but not able to connect because of your traffic issues. Traffic in the sense this channel traffic, not your road traffic. Okay, not exactly, Abnit. Whenever you have many to one, one to many, you can say mux and demux. Okay, because it is a transmitting, you can say it is a modulation. Modulator may be inside this circuit, and it is receiving whatever, say you can say demodulator may be present. So all these are some basic examples of your mux. We have enough examples. Let's move and understand how this mux fellow will work. How this fellow is able to do these many magics. Yeah, TDM is there. TDM is this one also. Time division multiplexing. 1, 2, 3, 4. Then again 1, 2, 3, 4. It is a round robin fashion. You will be connecting. Receiver also will receive in the same fashion. So let me continue. Start with a basic circuit 2 by 1 mux. What is 2 by 1 mux? Terminology you understand. 2 inputs, 1 output. I am not drawing this converging symbol many to 1. I directly take the rectangle. I hope you can understand. So you have 2 power n is 2. That is 2 power 1 is 2. So I will have only one selection input. So you have two inputs, I0, I1. Its position is given by name 0 or 1. And you will get 2 and 1 and y. So we are designing this. Now please understand, we are designing this box. This box should work like this. What is the work of this box? You have one selection input, I0, sorry, and you have one output. Okay, only one selection. These are data, these are selection inputs. This is your selection input. Here you assume 2 power n. What is n here in the 2? What is 2 power n? What is n? 1 na? 1 selection. So selection input can be 0 or 1. When it is 0, I want to select I0, and when it is 1, I want to select I1. You understand this logic? It is nothing but a digital switch. When selection input is 0, you can see it is just like a switch. When selection, based on the selection inputs, it will connect to any one of them. Okay, selection input 0, it will go to I0. When selection input is 1, it will go to I1. So it is very simple. Your what is your y is when S is 0, it is I0. When S is 1, it is I1. It is what we call characteristic equation of the mux. Okay, so now listen. Let me design this. So when S is 0, that is S bar into I0. And S into I1. This is the circuit which can do that job. 1 minute. This is I0 and this is I1, and give it to OR gate. Same equation, S bar into I naught plus S into I1. That will give you your Y. So it is simply, what is the circuit? AND OR logic. You can replace it with what? If you want to implement with NAND, this requires 3 NAND gates, this requires 1 NAND gate. How many NAND gates are required to make this circuit? To make a 2 by 1 mux, you require minimum 4 NAND gates. Because inverter requires 1 NAND gate and AND OR requires 3. Very good, very good, very good. So is it clear? This is the simple basic example of 2 by 1 mux. Next. Four by one mux. Okay, you have the 4 inputs 0, 1, 2, 3 and 2 selection inputs. I will give the names S1, S0. So what is this? 4 by 1. Because it is 2 power 2, 2 selection inputs and 4 data inputs. This is your function Y. Okay, yeah, 2 power 2 by 1. You can say like that. So here, what is your job? Let me make the truth table. S1, S0. When S1, S0 are 0, 0, 0, 1, 1, 0, 1, 1. What is your output? What is your output? Here it will select I0. Here it will select I1. You see 0, 0 is I0. I told already how to write the equation. S1 bar, S0 bar into I0. What is I0, sir? It is the information available at 0. It can be 0 or 1. It depends on the data you have here. It can be anything. Similarly, S1 bar, S0 into I1. A1 0 na S1 S0 bar into I2. S1 S0 into I3. Is it okay, everybody? Let me implement this figure. That is, not only this year, every year. Okay. Now see here. So first one is, what is that? S1 bar, S0 bar. S1 bar means here, and S0 bar into I0. This is your I0. What is the second one? Tell me. S1 bar. What happened? No one is commenting. S0 into I1. Next. S1 S0 bar, that is from here one line, and from here one line into I2. Lastly, S1 S0 into I3. Sorry for this font size. Okay. Now you connect them to a OR gate. That will implement your 4x1 mux. You understand this whole thing, whatever you have here, this will be present here inside this box. It will come to us with in a form of IC. Okay, so this whole thing, whatever you are having now, this will be inside this. Manufacturer will connect this and give it to you. Then you use it according to your requirement. Earlier only till now what we discussed, we proved only this will do this job. Out of the n number of inputs, it will select one input and give it to the output. This is proved. It will select according to this, it will select one and give it. 0, 1 will give you I1, 1, 1 will give you I3. Like that, it is selecting based on S1, S0, it will select one thing and give it to the output. That part is done. I told one more thing also. This magic box can implement any function. I told her it can do full adder, it can do full subtractor, half adder, anything can be done by this. I will prove that also, don't worry. Firstly, it is clear for you, it is what we call mux. So in the mux, please listen, examiner can ask you different questions. Let me give you the problems that can come in the mux. I will discuss everything. Okay. Listen, first one, types of problems on mux. Examiner can frame different types of problems. First one, the mux with delays. Second one, mux as universal gate. I want to implement means I should prove it as a universal gate, right? The third one, implementing higher order mux using lower order. The next they can ask, this is important. Gate point of view, this is the most frequently agreed point. Identifying function implemented by mux. Lastly, implementation of function using mux. They do reverse or this also. Okay. First thing is they may implement. They give you one figure. They ask you what is this function? What is the function implemented here? Second thing is they may ask you to implement. Both are possible. We discuss everything. All the models will cover it. Don't worry. So let's start. So, 1 minute. Want to start? Shall I start with first model? With NAND gate. Is 0.5. The output. Thank you. See the question. Okay, see the question. Okay, see the question. No problem, Aditya. Sir, NAND gate, if we have one complement appearing many times, we have A bar, it comes any number of times, only one time we count. What happened? Lag? Why this is happening? Okay, is it? Just read the question. You can give your answer because today no poll is conducted. Let me conduct the poll. If you are ready, I will conduct the poll. Okay? Ready? Abhinay, Deep, Robert, AD, Asif, Rutik, Deepak, Kashish, Deepanjali, and Sumit. Right answers. Okay, so let's start. So if you have, I'm sorry, if a 2 by 1 mux shown in the figure is having switching delay of 0.5 microseconds, then determine the output y. Just understand the question. Here, initially assume 0. Okay, just assume initially. So this 0 will come here. Please understand, this is your I0 and this is your I1. Okay. So you see, when I0 is 0 comes here, this switch will move here. Okay. Sorry, the switch will move from, the switch will be at this location only. When at this location, what is your input? Please don't understand this 0 and 1 are positions. This 1 and 0s are data. Please understand that. Okay. So when y is 0, this 0 will come here. The switch will move to this position. At this position, what is your data? What is your data? 1. That 1 will come in the out. Now this 1 will come here. Now 1 will come. The switch move from here to here. Then it is connected to this line. What is the data you have here? Tell me 0. Now this 0 will come. Again, that 0 will go back. That 0 will go back. And what is that? What is that? That 0 will go back. This switch will be moving to here again, and where you can have 1, and the process will be repeated. In this process, every time it is toggling, it is taking a time of 0.5 microseconds. So what is the total time period is the question, or what is the output? Okay, just wait. Just wait. Instead of analyzing like this, let me analyze simply like this. What is y? S bar I naught plus S into I1. You know this equation now? What is y? S bar I naught plus S into I1. Okay. Now what is y? S bar into I naught is how much? Please tell me. What is I naught? 1. What is I1? What is the answer? Y equal to S bar. What is the meaning of S bar? It is nothing but invert. Okay, it is nothing but your inverter. Now see here. So it is nothing but inverter. What is your Y? It is equal to S bar. But this Y is connected back to S with a propagation delay of 0.5 microseconds. This is the simple way to analyze it. What is the time period formula? 2n TPD. What is this called? Astable multi-vibrator. I discussed this area earlier in the basics. So 2 into n is only one inverter. TPD is how much? 0.5 into 10 power minus 6, which will give you 10 power minus 6, that is 1 microseconds. And then frequency is equal to how much? 1 mega. What is this norm? N equal to 1 inverter connected in the loop. It is called astable multi-vibrator, which will generate continuous toggle. I'm repeating, please understand. Two methods you can analyze this. First is initially assume some 0 or 1, your wish, randomly. 0 comes here, then the switch will be at I0. I0 is 1, so the data out is 1. That 1 will come here. Then the switch will move to position 1, that is I1. I1 is 0, then the 1 will becomes 0. Then 0 will come, again it will go to I0, that is 1 will come. So this is a continuous process of 0, 1, 0, 1, 0, 1. So your output will be toggling like this. But the switching delay given by examiner is 0.5. So for on 0.5, off 0.5, total how much? 1 microsecond. So the frequency is 1 megahertz. This is one method. Otherwise, take the characteristic equation, substitute I0 and I1. You can prove it as this circuit is nothing but an inverter. Then you can connect inverter in a loop, which is nothing but when n is equal to odd, it will work like a astable multi-vibrator. That we know it already. Formula is 2n dPd is the time period. Frequency is 1 by time period. So is it clear? Very good. One more question. No, because every time your output is changing, na? When every time output is changing from 0 and 1, it will change. Na? When it is 0, switch move to 0th location. Okay, when it is 1, but at 0, I connected 1. Yes. You understand, Ruchi? At 0, we connected 1. So data comes as 1. Again, this 1 goes, but 1 at 1, again 0 is connected. It's a continuous process. Right, Rishi? One minute. %, gave right answer. And Deep, Eddie, Sumit, Asif, Dhanpal, Ashish, Daniel, Sadbhavana, and Jahra. Very good. Now you tell me, what is this circuit? It is nothing but when n equal to 5, it is odd. It is astable. Then what is the time period of the clock? Direct formula 2n TPD, which is 2 into 5 into 10 power minus 12, which is 10 power, sorry, into 100, no? 100 picoseconds. 100 into 10 power minus 12, which is 10 power minus 9, 1 nanosecond. Now your frequency is equal to, what is the frequency? The frequency f is equal to 1 by 10 power minus 9, which is 10 power 9, 1 gigahertz. Whether you take the output here or here, it doesn't matter. All are same, man. It is a cycle. Okay, you take here, you just round it differently. That's all. It doesn't change whether you take the output here or here or here or here. All are same. Okay, it may here may be 0, here may be 1, that may be different, but that cycle will be same, time difference will be same. Please understand that whether you take the output here or here, your frequency will not change. Please understand that. Is it clear? Some people gave 0.2 because it is after 2. No, whether you take here, here, anywhere, your frequency is the same. Okay, Shivam, I already told what n equal to even. Everybody tell me what is n equal to even. That's all. It is like a round cycle. Actual sense, you can read like this. Where you take output doesn't matter, man. Okay, it's a cycle. Whether you take here or here, do you have any difference in the frequency? It's a loop. Ah, bistable can act as a memory storage element, Amitabh, that we discussed in the sequential circuits. Your bistable is the basic element in your memory, okay, but you have extra control inputs like set reset that we discussed in the sequential circuits. So let's move further. Can I give one more question? Similar model. Okay, get ready, I'll make the question. Okay, if time period t equal to, I'm sorry, if TPD of each, I want to refresh or that Rishi need to refresh? I need to refresh? Okay. Okay. If the propagation delay of each mux is equal to 1 second, then output y is equal to how much? Option A, square wave of 0.1 H. Get ready. I want 100% here at least. Square wave of 0.2 H. It may be constant at 0, constant at 1. Option E, none. Okay. Assume initially y equal to 0. So just read the question. I will start the poll. I also need to check the answer whether it is same. Fine. So let's start the question. Start the poll. Get ready. Very less people write answers. Yes. Eddie, Danpal, Anupama, Manjunath, Robert, Chaitanya, Sagar, Deep, Sumit, and Asif. Right. Here, please observe one observation here, clear, important thing. This observation is required. Okay. Here, if you give for 0, 1, and this is acts as a inverter. Okay. 1 minute, please. I'm sorry. I made a wrong thing. Here, what is this? Here, what is the answer? Here it is a buffer. Okay, here it is a buffer. Only this is an inverter. This is a buffer. This is a buffer. Please understand. Okay, so forget about that options. It is like this. I I I I typed the wrong answer, but the question is correct. I think less people gave that right answer. Just wait. Okay, so buffer. This is buffer. This is inverter. Here, what is the number of inverters here? One only. Okay, so number of inverters is 1, so it is odd. Okay, what about this, sir? Please understand, this is like this. You have a buffer and inverter. Buffer is 4 seconds, inverter is 1 second. Why it is buffer? Don't worry, I will explain it. For time being, leave it. Okay, so if you give here, start with some 0. Okay, this 0 will coming here. After 4 seconds, you will get 0 here. After 5 seconds, you will get 1. At what time? 5 seconds. Okay, then this 1 will come here. After 4 seconds, and 5 plus means 5 plus 4, how much? 9 seconds. You will get this one as it is. And another 1 second, at 10 seconds, you will be getting 0. So again, this 0 will come here. After another 4, that is 14 seconds, you get 0. And another 1, 15 seconds, you get inversion. So it is the same. Okay, it is on, off, on, off. But here, what is the time period? Is 10 seconds. So what is your frequency? 1 by 10, 0.1 Hz. So who is the right answer here? A is the right answer. Okay. Even actually you don't know the question also. So unfortunately here you get the same thing. Originally you should observe here. This is okay. Originally actually problem is originally even you don't know the trick blindly if you do also the same answer. Unfortunately the data is like that I have taken. If I change something it will not be same. Okay, so please listen here. I have given actually reverse. I will change the question now. I will explain again. Don't worry, just listen here. If you have a buffer, if you have mux, if 0 is connected here, 1 is connected to the 2 by 1 mux. What is your y? Y equal to S bar I naught plus S into I1. S bar into, what is I naught here? Tell me friends, what is I naught? I1 is 1. That is, yes, this is what we call buffer. But if I make something like this, here 1, here 0, that is I0 equal to 1, I1 equal to 0. This is Y equal to S bar. This is what we call inverter. This is inverter, this is buffer. You should understand the difference. Okay. So originally what I want to give is this question. I want to make all inverters except one buffer. I want to give this question. What is the question I want to give? Four inverters, one buffer. This is the example I want to give. N equal to even output constant at initial value 0. This is what I want to give. Is that clear? This small 0 1 change will convert buffer into inverter or inverter into buffer. Please understand that concept. You should observe properly. If examiner is clever enough, he can trap you easily. So fine, let's move. Let's take one more question given in one of the gate paper. In the logic circuit shown in the figure, if each mux is yes, inverter will decide having delay of 1.5 nanoseconds, NOR gate delay equal to 2 nanoseconds, inverter delay equal to 1 nanosecond. Determine total propagation delay. So let's do this question. 2 nanoseconds. This is 1 nanosecond. This fellow is having 1.5 nanoseconds, 2 nanoseconds, 1 nanosecond, 1.5 nanoseconds. Okay. If you are ready, I will start the poll. Okay. So let's start the poll. Get ready. Only 15% gave right answer. Very less. Anupama, Dhanpal, AD, Alicha, Manjunath, Robert, Chaitanya, Sagar, Deep, and Deepanjali. So let's see where you people are. 7 is the very favorite answer, wrong answer. Don't add blindly. 2 and 1.5, 3.5, 3.5, 9 is the right answer. Sorry, 7 is the right answer. Or don't add all and say 9 is the right answer. Both are wrong answers here. So let's do the question. Okay. So somehow I copied this and pasted here. So please listen here. If S equal to, two possibilities are there. Your selection input is there, na? Selection input. This selection input can be 0 or 1. Two possibilities. Everybody accepted or not? So let me take S equal to 0 first. If S is 0, what is your path? S bar will be how much? 1. So when S is 0, this is the path you should follow. This green line is your path. Can you tell me what is the delay in that line? 2, 3.5 and 4, 5 nanoseconds. Why 6? My dear, you may have the doubt like this. Sir, this one also included. No, listen please carefully. At time t equal to 0, you applied everything. Assume you applied this at a time t equal to 0. At 1 nanosecond, you will get this. And at how much time you will get this one? Tell me here, 2 plus 1.5. How much time you get? At 3 point. So in these two, don't add these two. These are parallel operations. This is doing independently. This is doing independently. You take more maximum of these two. What is maximum of these two? Comment 3.5. So plus 1.5. You understand or not? In the time t equal to 0, 1 nanosecond, you are ready with the selection input. But this fellow will come lazily. At what time? 3.5. So don't add 1 and 3.5. These two are parallel things, not separate things. That is, if you see the timeline, this is 1 and this is 3.5. Okay, it is part. Okay, same way. Don't take this is 1 and another 3.5 and take 4.5. Wrong. I have not decided, man. Please see, Rishi. When SC is 0, when SC is 0, who will select in the mux? You tell me 0 will select or 1 will select. When SC is 0, who will be selected at 0 line or 1 line? Okay. Is it okay? 0. Okay, then at 0, you have one NOR gate which requires 2 nanoseconds plus 1.5. 3.5 will be ready, but already you are waiting from 1 nanosecond. Okay, 3.5 plus 1.55. So how path is decided? Based on selection input. Selection input is 0 here, 1 here. That's why I selected this and this. Similarly, second possibility is there. What is that? If S equal to 1. When S equal to 1, what happens? If S equal to 1, this 1 bar, what is 1 bar? 1 minute here. I need to just 1 minute. It is not working. Yeah, finally it is working. Listen. So when S is equal to 1, I hope you already done this, but I will explain. It will be 1 bar. You give 1 here, which is 1 bar is 0. So if S is 1, this is Rishi, you asked me path now. Now what is your path is this one. When S is 1, S bar is 0. 0 means this line. This is your path. Now in this path, what is the delay? Just add it all. 1.5, 1, 2.5, 4.5 and 6 nanoseconds. So here 6, here 5. Take maximum of both. That will give you your answer, 6 answer. Okay, because you understand here, when first NOR gate is selected, second will not be selected. When second is selected, first will not be selected. Because of this logic here, don't add both the NOR gate delays. That is the logic here. Is this point clear? When this NOR is active, this NOR is not active. When this NOR is active, this NOR is not selected. That is the reason. Because of MUX will not select both the inputs at a time. It will select any one of them. Any one of them. So what is the right answer? Is 6 nanoseconds out of the maximum of 5 comma 6, which is 6 nanoseconds. I want to provide you one key I have already given in the group. So any kind of doubts you are ready, you can ask. Just give me 1 minute. Yeah, I got it. Now, one minute, Rohit, I will answer you. Just So this is the key. I forgot to provide you for 30 questions DPP. That is SOP POS. Last DPP I forgot to give you. Okay. Today I'm not providing because until MUX is completed, I cannot give you more questions. That is the issue. Okay? Once MUX is completed, I can provide you the questions. That is the issue. Next class I will provide. Next class means tomorrow doubt session not able to provide. Day after tomorrow. Okay. So Deep, how to save from trap? Okay. So if you are trapped, I am happy, you should also happy because you have committed the mistake which you can avoid in your exam. That is the intention of the trap. You will also feel okay, you are doing this kind of mistake, you should not repeat. My intention is not unintentionally do make you the mistakes. That is, it should be logically. I am happy for your traps so that you learn something. You don't do that in the exam. That is the intention. Yeah, group I provided number systems. Na? Yes, I have seen your message. I will provide you the Boolean algebra also. Okay. So yes, Asif. Why? Because our discussion is not complete. I don't want to add the questions. That's why. Okay. Please message me, Ganesh. I will check it. I will add you. Okay. I will give you the details. Don't worry. You have already messaged me on Unacademy app. Na? Yeah, no problem, Rushi. How it will work as a buffer and inverter. One more thing, Rohit. Rohit or Rahul, I confused Rohit only. How you got 2 into 1.5 plus 1.5? Your answer can be coming anyway, but logic should be true. Okay. You cannot say 2 into 1.5 plus 1.5. Here the logic should be 2. Okay. Because if it is 2 and if it is 5, the same case your answer may not come. Once you develop the logic, the answer should be true for anything. If I change this to 8 nanoseconds, for example. Okay. So every case it should come. That key is for a previous DPP I provided long back. I mean 4-5 days back. I forgot to provide you the key. Yes, Rohit, check it. Roshi, I will answer your doubt. Don't worry. Any other doubts you can ask me. Thank you. Thank you very much. Good night. So Rishi, please check. What is that bomb night? Thank you very much. Your MUX only one model is completed, man. 4 models are left. Please remember that. MUX has a universal gate. How to make MUX has different implementations, and all those things will come in the next lectures. Good night, Ronald. So, any other doubts? Anyone having any doubt? Please ask me. Otherwise, I will end the session. Buffer and inverter combination, please again. Please check it here itself. Alicha. I am in that slide only. Okay. Firstly, understand. Yes. Why it is working as buffer and inverter? You should understand this point first. Okay. Is it you accepted these two? In these two, if you don't have doubt, I can proceed. Otherwise, I cannot proceed. When I naught is 0, I1 is 1, you place in the equation I naught 0, I1 1. Y is same as yes means it is like a buffer. Okay. Wait, Harshvardhan, I will clear. Okay. Similarly, when let me complete this, then I can come to your doubt. I naught is equal to 1, I1 equal to 0, it is an inverter. Now the question is simple. This is an inverter, this is an inverter, this is a buffer, this is inverter, this is inverter. So two inverters, one buffer, two inverters. Four inverters. So you start with 0, it will come 1, 0, again 0, 1, 0. Wherever you started, ended it the same. Got it? So if one inverter and four buffers, it does reverse. That's all. So Harsha, what is your doubt? In the last question. Okay. Yeah, tell me, Harsha. If sir s equal to 1, input we take 6 nanoseconds. My doubt is R input is initially present, then why it's time constraint? R is present, but R bar is required, na? Harsha, R is present at a time t equal to 0, but R bar will come at what time? 1 nanosecond. Because your input is not R bar, where you have one inverter. This is the last question, man. Harsha, is it clear? R is available at t equal to 0 only, but R bar will be available at what time? 1 nanosecond. Because when you give s equal to 1, it should wait for a time t equal to 0. It should wait for R. Okay, R is ready, but R bar will come at 1 nanosecond. Then it will give it here. So 1 plus 1.5, 2.5. Then once you give this input, another 2 is required for him, 4.5, then 1 point. Is it clear? Your doubt clear? Vasishtha, listen here. Whatever may be the gate, don't worry. If you're in this case, a simple understanding is your selection input is 0 and this is selected. Out of these two inputs, whichever comes late, you consider that because they are working in parallel. So this fellow will come at 1 nanosecond and this fellow comes at 4.5 nanoseconds. So who is coming late? 4.5 coming late. So we consider this. Two people are there. One comes at 4.5, one comes at 1. Okay, but both of them, if you take who is coming late, means total is 4.5. One minute. Anything you should consider everything, not inverter or XOR gate or NOR gate. You consider everything, okay? But in that, whichever takes more time, that will be considered. Simple rule. Because it is an inverter, because it is NOR gate, I don't have any favor. This fellow is ready. Okay, he wake up and ready by 1 nanosecond. This fellow need to tayar. He should ready by 4.5. So out of them, who is coming late, we should wait for him. Any case same. Okay, selection input is ready by 1, but this fellow is coming lazy at 4.5. We should wait for 4.5, then proceed. If he is ready at 0.5 itself, then we take 1 into consideration. If he is ready at 0.5 itself, then we take 1 into consideration and 2.5 is the answer. So here the value, whichever is more, that will decide. Okay, so two people are getting ready, man, UAB, and both should be ready. This fellow took 4.5, this fellow took 0.1. So out of X, Y you take. X and Y, two people we should get ready. X takes 4.5 seconds, Y takes 1 second. So how much time you should wait means 4.5. We don't say na 5.5 or 1. It depends on who takes more. We should wait for the second bill. Hello, sir. Good night. Saurav, you see, two cases I analyzed. What is the first case when S0? When S is 0, S bar is 1. So this path. Second case, when S is 1, S bar will be 0. So this mux will select any one of them, not both at a time. Now, Saurav. Okay. When this selection input will tell that. Ganesh, I have seen. Let me clear the other doubts, then I will come to you. Don't worry. Is it okay? Fine. Now come to Ganesh. What is your doubt? Yeah, what is your doubt, Ganesh? Sir, in the right half, even number of ones, then X naught, sir. Not right half or left half. This one, yeah. Yeah, you can, you are saying this part. It is having even number of ones for all minterms. Not even number of ones, even number of zeros. I don't know whether you followed all my classes or not, Ganesh. Please comment that part first. Is it you have followed all my classes or not? Yes. What is XNOR? It's not even number of ones, it is even number of zeros. If it is even number of ones, it is a complement of XOR. It need not be equal to XNOR every time. It will be equal when you have even number of inputs. Okay, fine. That's all. Let's end the session. We'll meet tomorrow, same time. Thank you. Bye bye. Good night.